Welcome back, Physical Science 20. This is the first section of the HT1 unit, 6.1, Warmth and Coldness. So the first part here, we're looking at how can you accurately measure warmth and coldness of objects. So to kind of look at how we currently look at that, we have to look at how historically we looked at it. It was thought that warmth and coldness were produced by something referred to as caloric, a massless fluid that went from warm objects to cooler objects. So a cooler object could become warmer with the passing of this so-called caloric from the warmer object to the cooler object. But of course it didn't take long to realize that we don't necessarily have to have a warmer object and a cooler object for heat to be transferred, because if you look at rubbing two surfaces together, such as your hands, it gets heated up. So that theory was abandoned in favor of the kinetic molecular theory. And of course the word kinetic, just like kinesiology, etc., kinetic implies movement, moving molecule theory, kinetic molecular theory. So the matter is composed of particles, be it atoms, molecules, etc. They attract each other and also have kinetic energy or moving energy. So if we look at something that's a solid, the atoms and molecules can move a little bit. They can vibrate back and forth. If you ever hit a table with your hand, you can feel the whole thing vibrate. So that shows that they are capable of vibrating. And of course, if we were increasing the motion of those particles, make them move faster and faster and faster, it could change the state and become liquid, etc. So if we look here, according to the kinetic molecular theory, an increase in the motion of the particles of a substance makes the substance feel warmer. A decrease in the motion makes the substance feel cooler. So if you can make the particles move faster, we register that as the object is feeling warmer. If we can slow down the motion, the object feels cooler. Okay, so if we look at so that was a solid. If we look at liquids and gases, and a liquid, they have much more kinetic energy than a solid. So here you can see the vibration of the solid. Here, liquid, there's much more movement. Liquids can flow since they can move so much. And in a gas, particles are moving quicker, and of course the distance between the particles gets bigger. If you look here, the distance between atoms, molecules, and the liquid are much further apart than a solid because they're moving quicker. Over here, moving quicker still, therefore the separation between them gets even greater. Okay? So that is kind of how the kinetic molecular theory applies to solids, liquids, and gases. Okay? From there we move on to thermal energy. So kinetic energy is associated with how the atoms or molecules are moving, but there is also a stored energy present as well. Potential energy is associated with the force of attraction between particles in the substance itself. So if we have a combination of the moving molecules and the stored energy associated with the attraction between particles, we get thermal energy, which is the total quantity of kinetic and potential energy that atoms or molecules possess. So of course, if we absorb thermal energy, the object warms up. When energy or thermal energy is released by a substance, it cools down. Okay, so thermal energy is what we're looking at there. So back to here, temperature and thermometers. Temperature measures average kinetic energy. So if you have an object such as a glass of water, the molecules of water may have different kinetic energies, some larger than others, but on average, what is the average kinetic energy? And you can measure that by taking the temperature of it. So temperature is a measure of average moving energy or average kinetic energy of the substance. And the key word there is that it's average, because of course all molecules are not going to have the same exact kinetic energy, but on average, what do they have? Okay, so if we look at a thermometer, an older thermometer here, it results as a collision of particles between the alcohol that we use to read what the temperature is, the glass, and the atmosphere around it. So if we're looking at how does the temperature, or how does the thermometer liquid go up, if you look at if it's hot outside, the particles are moving faster than if it were cold out. So colliding, which of course collides with the glass bulb. The bulb vibrates much more drastically, causes that energy to be transferred to the alcohol in the thermometer, and if that temperature is going up, the particles move faster, and as they move faster, they spread out more, and of course, taking up more volume causes the liquid to go up in the thermometer. If we look at what happens if it's colder outside, so we have a thermometer that could be inside the house, we move it to outside the house when it's cooler, so the thermal energy will be higher in the alcohol liquid here, and of course it's cooler out here, so there'll be a transfer of heat out, so the molecules speed up the glass and then exit out. So if we're losing thermal energy, what happens is that the molecules here will slow down gradually because the thermal energy is leaving. So if they slow down, they get closer together, so that causes a drop in the liquid of the alcohol or whatever is being used for the thermometer. Okay, so the kinetic molecular theory can be used to describe how a thermometer works. If it's hotter outside, the thermal energy goes into the liquid, thermal energy speeds up, spreads out. If it's colder outside, the thermal energy is transferred out to the exterior. For losing thermal energy, the molecules will then slow down and then contract and causes the level to go down. All right, temperature scales, 3 temperature scales we're going to look at. So we have the Celsius scale, named after Andrew Celsius, based on the freezing point and boiling point of water. The Fahrenheit scale, based on the freezing point and boiling point of salt water. And then we have the Kelvin scale, which is based on absolute zero, that temperature in which all molecular motion theoretically stops, so all the atoms and molecules stop vibrating because it's so cold they just contract and lose energy and basically stop moving. Now that occurs at minus 273 degrees C. So if we were to take minus 273 degrees C, the lowest possible temperature, and add 273, we come up with 0 Kelvin, which is the lowest number that is reached on a Kelvin scale. Now that comes in handy in other concepts in which we don't want to deal with a negative temperature. So often the Kelvin scale is used for that, dealing with calculations in which we don't have to deal with the negative temperature. So if you take a look here, if you take your degrees Celsius temperature, add 273, you get Kelvin temperature. Or if we rearrange this equation to get degrees Celsius, take your Kelvin temperature, subtract 273. Okay, so relatively easy calculation there. As illustrated here, if the alcohol boils at 78.3 degrees C, what's this in kelvins? So Kelvin is equal to degrees C plus 273, 351 Kelvin. Or if the alcohol freezes at 159 Kelvin, what is this in degrees C? So degrees C is equal to the Kelvin temperature minus 273 minus 114 degrees C. So you can run through these practice questions yourself. Relatively easy. Here we're going from degrees C to Kelvin. So of course this is the relationship. And over here, converting the Kelvin to degrees C using that formula simply rearranged. So I think you can run through that. The answers are there. All right. Lastly here, thermal energy, temperature, and physical state. Some substances increase in temperature when they absorb thermal energy and decrease in temperature when, of course, you release thermal energy. If we look at the temperature at which a solid melts into a liquid, that's the melting point. And if we go vice versa, a liquid freezing into a solid, that is the freezing point. And for most substances, those are the same temperatures. So if we look at water, that of course is 0 degrees C. Boiling point, the point in which a liquid turns into a gas, is a boiling point. Vice versa, gas turning back into a liquid is the condensation point. And again, those are the same for most substances. And of course with water, that happens at 100 degrees C. Okay, so summary, thermal energy is the total potential and kinetic energy. Temperature measures kinetic energy, that part. And of course, if you gain energy, the temperature of the substance goes up. If you lose kinetic energy, the temperature of the substance goes down. And then we have the 3 different temperature scales and the relationship between the Kelvin and the Celsius temperature scales. Okay. The questions I want you to do here are all of them except for number 5, where it talks about researching the caloric theory. We can maybe do that later on in the course. Number 4, the only calculation here is in question number 4, where we use these relationships here, the Kelvin and Celsius temperature scales. Okay, so 1 to 7, omit 5. We'll see you again.